thank you for kind invitation and the introduction. And I'm very happy to introduce our smart materials research. And today I would like to introduce our research in the flexible actuating materials for wearable application. And this is the outline. First is the research background. And then I would like to introduce two kinds of actuators, which we think can be used for wearable applications. The first one is no voltage driven electrochemical actuators. The second is the visible light responsive actuators. And then we would like to introduce some we try to reconfigure this low V actuator into fabric or into yarns for purpose of wearable applications. And lastly, I would like to introduce the surface cooling due to the actuations. And firstly, I would like to introduce the concept of the actuating textile. It is a new type of wearable muscle for future wearable technologies. Actually, it is a fiber assembly with dynamic properties. Its cool dynamic mechanical output include form change and include enough force generations. And it often work together with the sensor to control the rigidity and to achieve the move and the hold operations. Usually, it can be regarded as a robotic fabric and can achieve many applications. For example, here is a cartoon to show the use of actuation textiles. You can see the actuating textile can help us to trace and can apply the force on our human muscle to assist the locomotion and to assist to grab or reach something. And also it can generate other functions such as thermal regulation, haptics, and medical therapy. So we think these functions are very useful to those people who are disabled who have some special diseases. So it's have very wide applications. Until now, we know there are many types of materials can be used as actuators. From this table, we can see classified by the energy source. There are some electrical actuators, some heat actuators, and some light actuators. And for the materials, we can see the materials can many be made with polymers. In order to use them for wearable applications, which close to human body, so these issues should be addressed. For example, if we use the electrical actuators, the current or the voltage should not be high, should be safe to human body. If you use the heat actuators, so the temperature cannot be high. So this question, safety should be the first important issues we need to address for wearable applications. Then the challenge will include the integrations. We call the textified. It's better for those actuators can be integrated with our clothings. And the next challenge would be the performance. Can we control, can we get the high performance of those actuators? Here is our first work for the wearable applications. it is the actuation caused by the ion migrations. The biggest advantage is these actuators can be achieved on the very low voltage, And the left pictures is the structure of these devices. Very simple structures, has sandwich structures with electrolytes and electrodes. So when the mechanism is when applied electric fields, the ions will polarize, will transport, and will accumulate at the electrodes. And due to the asymmetry expansion of the electrodes, we can see the different degree of actuations. And in our first publications, the carbon nanotubes was used as the electrodes. So we know, compared with the metals, it should be high conductive and highly flexible. And also for the electrolytes, we use the iron liquid. The best advantage for iron liquid is it can has very wide potential window and has high ionic conductivities. So compare with the hydride ions, we do not need to worry the hydration of the electrolysis of the hydrate ions. So it's our design for this ion migration induced actuations. As highlighted in the Nature Asia materials, the biggest advantage for this kind of ionic devices is it can be light, flexible, and no voltage driven, show promise for implantable or wearable applications. But also it has the biggest disadvantage, compared with electro devices, due to the no ion mobility, the device response is quite slow. Yeah, it is the first challenge. And then due to the soft polymer modulus, the mechanical output is also quite low. That means the no force output cannot support the enough mechanical work. So in order to address this issue or to overcome these disadvantages, we need to understand the basic process in the ionic devices. So we think two things are important. One is the ionic transportation. The second is the transportation channel. Yeah, as shown this cartoon, we think it's difficult for us to change the intrinsic mobility of ions. So in our following works, we focus on the research on the ionic channel design. As shown in this figure, you can see if the pool size is too big, so it's also quite difficult to generate the deformation. Yeah, and also you can see if the if the channel has very much active size, it can attract much more ions to be absorbed, to be generate much high deformations. So it's our basic idea for address the disadvantage. Yeah, in the following work, we fabricate different kind of high quality porous nanoelectrodes in our lab. Here is the high quality has two meanings. The first means we can control the microstructures of the nanoelectrodes. For example, the CNT can be oriented, and also the MOV structure can be strained with the CNT to keep the good conductivities. So due to these best microstructures, The second meaning is for the high quality is they have high quality in the electrical properties and such as high electrical conductivity and no interface impedance. And also these nanoelectrodes can show very large specifics of surface areas and has important suitable pore size. And due to its kind of electrochemical devices, it also has very high competitiveness and also have high electromechanical stabilities. And okay, this is our recent work, try to make them in large scales, yeah, by using just simple van der Waals interactions. So we can see the graphene film with metal lusters can be easily achieved due to the van der Waals assembly method. And this method can be achieved on the surface of porous substrate, on the smooth substrate, and on the elastic substrate, and even on the fiber substrate. And in this video, you can see these devices can be robust. Yeah, can be called deformable devices. Okay, after using these nanoelectrodes, we can easily achieve the large deformation under very low voltage. From these two figures, we can see the strain and the stress can be increased due to the increase of specific surface of areas. That means it's a linear response with SSA. The best results is achieved by the MOV structures, because the MOV structure has the highest SSA in our nanoelectrodes research. However, this picture shows we can easily achieve the large deformations, but the large deformation usually needs long time, such as tenths of seconds or minus tenths of. In order to address the snow issues, in our lab, we use another kind of electrodes. It's a kind of two-dimensional graphite carbon nitride nanosheets. You can see in the nanosheets, they have many active sites. And our idea is to using the active sites to increase the interaction between the electrodes and the ice. Okay, the direct evidence can be shown here. You can see the capacitance was increased significantly due to introduce the active sites. Then we can achieve very high, very fast and powerful actuation without losing the large deformations. Besides, in this work, we also using a kind of double network of copolymer. One is PEVO, another is NBI. We can achieve the high ionic liquid uptaking capability, and also can achieve the high ionic conductivities. Based on these ideas, we further fabricate a kind of another electrodes. It's a kind of carbon nanotube array electrodes. The idea is to using this structure to shorten the ice transportation distance. You can see in these figures, if the carbon nanotube electrodes is not oriented, so it's very difficult for the ice to transport into the electrodes. Yeah, obviously it will take long time for the ice transportation. But if you use the oriented CNT electrodes, so the time will be decreased. So from this figure, we can see the best response frequency we can achieve is around 40 hertz. And you will see the 40 hertz almost can close to the vibration frequency of the dragonfly. So the idea is if we can using the active sites and the optoelectrodes, we can achieve much more faster ionic actuations. Now you will see the 40 hertz is not too fast compared with the electron devices, but for the ionic devices, it's will be the faster than before reported results. The above is the result meaning based on the ions physical adsorption and desorption, and then the expansion of the materials. Next, I would like to introduce a kind of actuation caused by the chemical bond change. So from the previous report, we can see previous theoretical report, we can see if the carbon or graphene changes the carbon bond, usually we'll need very high charge injections. For example, here is per astron, usually we need 0.1 volts, and here is per carbon astron, we usually need to 0.02 or 0.04 electrons. That means they usually need a very high energy charge to change the carbon chemical bond. So it's almost cannot be realized in our experiment. Recently, we report a kind of a new carbon and the new mechanisms, which the actuation can be realized under the very mild conditions. Here is the new carbon is graphene. Compare with CNT and graphene, the graphene has many active, highly active acetylene linkage, and also has very special absorption models and absorption states with the ions and also we found that the alkane bonds can change to the alkane only by cations absorption and the coordinations, and this can be achieved only by several volt conditions. So this new mechanism is called alkane-alkyne complex transition effect, and the transition can lead to the dimension change of the covalent bond in graphene as high as 17.36%. And we think this provides us a new way to think and design the high-performance actuator at molecular levels. Here is the fabrication of materials and devices. I would like to skip this and mainly to introduce how we verify the effect, the molecular activity. The first tools we use is SFG. The full name is Sum Frequency Generation Spectroscopies. Here is the schematic of the setup of the SFG. We use 2 beams of laser to focus on the interface of the electrolytes and the electrodes. If the tiny structures change, we can detect the change by the sum frequency generation spectroscopies. Here is a setup of the experiment. And in the right, we can see in these regions is mainly for the alkane vibrations, and this region is for the graphene characteristic peaks. So you will see if we don't apply voltage, you can see the typical peaks showing the red is for the graphene is appeared, is there. And if you apply a voltage, so you can see the peak, the red peak is disappeared, and the blue peak is for the graphene is appeared. So we can verify the molecular activity. That means alkane and alkyne transitions under the electrical conditions can happen. We call the alkane alkyne complex transitions. And recently, we're using another kind of conventional method. We're using Raman also to verify the molecular activities. Here is the materials. We synthesize the graphene directly on the surface of the copper, and we set up these testing conditions. We also can easily to verify the appear and disappear of the characteristic peaks of the graphene. Yeah. Finally, we test the high performance in microscopy and obtain the mechanical power, output mechanical power and input electric power, and we achieve the highest transducing efficiency can up to the 6% due to this special ACT effect. And this value is far exceeds with current transduction efficiency. Normally it's below 1%. And also we want to fabricate this low voltage actuation materials into the yarns or fabrics, which can be close to wearable applications. The first examples is the no voltage actuation yarns. There are two methods used in the fabrications. The first is we're using the electrospinning to fabricate the electrolytes layer, and also we're using the twister method to obtain kind of electrodes, and then we're using the self-plying method to assemble these devices, and then we apply a voltage. We can observe the actuation of the no-V yarns, actuation yarns. And due to the twist and bundle structures can enable the robust yarn muscle achieve the highest isometric stress of 10 to 8 megapascals, which is 31 times of skeletal muscles. And also another examples, we're using conventional such as ink printing and the screen printing method to fabricate the no-V fabric muscles. Here is the typical structure of the electrical structures. You can see the electrodes, the ionic polymers can be printed on the surface of the fabrics, and we can achieve different kind of modes of deformations due to different electrodes location design. Okay, the above is meant to introduce kind of output, mechanical output. Here, I would like to introduce another output is optical output due to the mechanical output. That means the ionic actuation can induce the temperature decrease. Here is our picture to show under thermal detection, the object can exceed the temperature decrease from 32 to the 27, almost 5 degree decrease. And this temperature is very close to the background temperature, 26. And here is our devices. Similar with our previous electrical devices, we're using graphene as working electrodes and using nano PE containing ion liquid as electrolyte layers. And also we're using the gold counter electrodes to compose our devices. And obviously, we can observe the actuation. The actuation is present by the thickness vibrations on the 3 volts, And we can see only after 2 voltage, the vibration can be brought out. And here is for the in-suit optical spectral measurement, we can see after 3 volts, the reflections can be increased significantly. And after calculations, we can observe the best results. That means the emissivity can decrease to the 0.1. The reason is obviously the 2D graphene can make the ions inclination and cause the actuation. And also the ions can shift the energy level and change the optical properties, and then their emissivity and the thermal radiation control. Here, the value for the emissivity around 0.1 means the graphene film can reflect 19% of the thermal radiations. If you use the devices for thermal camouflage, that means just to show in the last slides, the object can exhibit nearly background temperature under the thermal detector. And here shows the change is reversible due to the applied voltage. The emissivity can be reversible change. Another story I want to introduce is ions migration not only can achieve the actuation, but also can achieve the sensing functions. Here is a picture to show the basic principle. Here is ionic gel. If you apply a force in the ionic gels, due to the transport of the ions and due to the volume change, so the ions concentration between the 2 locations shown here is different. Then the potential gradients is generated, as shown in here. Due to the deformation, the potential is generated. We call it the piezo ionic effect. And compare with the other capacitance or resistance principle, our sensing principle is quite unique, such as we do not need the electricity power, it's a self-power. And also it can recognize the directions. If you upbending and downbending, we can recognize the directions of the bending directions. And we can, next we will verify it can also to detect the large deformation and also very tiny deformations, and it can be integrated with our wearable clothing or some other accessories. Yeah, here example. If we integrate with integrate this ionic sensor into globe, we can easily recognize the sign languages, and also can translate them into some digital signals. The main reason, due to time limit, the main reason is due to the glove can detect the finger motion and the wrist motions, and can combine these signals to recognize the sign languages. And also we can using the glove to control a robotic hand and can detect our pulse for diagnosis purpose. And finally, I would like to introduce our second actuators, is night actuators, as introduced before, because night is also an achievable source in our daily life. So we spend some time for this kind of actuators. As shown in figures, we can show, compare with the electrical actuators, we have much more choices for the night sources, such as we can using different wavelengths to stimulate the actuator. Also, we can using the polarized light as a night source to stimulate the actuators. So our motivation is to find some photon responsive components and bring this deformation into the micro photo actuator, microscopic photo actuator performance. Next, I will give some examples. The first is the UV responsive. We're using some molecular nanocrystal assembly. It's a sheaf based. The reason is based on the photoisomerizations, and we can achieve the actuations under the 365 UV radiations. And next example is the visible light actuations. And it is based on the gold nanorods due to different aspect ratio and the different local surface plasma resonance and photothermal effect. So we can find the actuator can tracking the light, just like the sunflower can track the light for future adaptive devices applications. And last one is the heat actuators based on RR wavelengths. This is a structure, is asymmetry biomorpho structures, many made by the nanocarbon, like graphene. Due to graphene has very wide spectral absorptions, a high photothermal conversion efficiency, and the negative thermal expansion coefficients. So we can easily achieve the photo actuator, even the visible light locomotion performance. Okay, I think that's all for my today's talk. For short summary, we think these two kinds of actuators, that is the electrical low voltage driven actuators and the visible light actuation technologies will have great impact on the smart wearables and smart living applications. And we think for create some groundbreaking progress and for bring out some innovation applications, two things are very important. One is new materials, new actuation materials. Another thing is we should develop some new devices, structures can help us to bring out these applications for future wearable devices. And finally, I would like to acknowledge my collaborators, my previous group members and current group members, and also the financial support. Thank you very much.
Hi, Professor Chen. Thank you very much for your fantastic talk. Yeah, this is Wei at NTU. Actually, I'm very interested in the ionic material-based actuators. May I ask how you design these ionic materials? Are there any principle that can share with us? Thank you.
Okay. Thank you for your very good questions. Maybe the time I cannot express very clear. This is the pictures for the structures and the materials and the principles. Actually, the structure is very simple, just like devices, just like a supercapacitor or the lithium batteries. two electrodes and salvage the electrolytes. And when we apply the electric field, the cations and anions will polarize and transferred to different directions. And due to the big size difference with the cations and the anions, so the expansion of the electrodes will be different. So due to these principles, we can achieve the ion migration induced actuations. So our work mainly focus on the different nanoelectrodes and the nano channel design for achieve the such as the speed, such as the efficiency, performance for the ionic actuators. Thank you.